So, good evening, everyone. My name is Pranam Mahajan. I am your TA for this course. Let me introduce you myself. I am a PMRF scholar in Department of Civil Engineering from IIT Madras. So, we are given this opportunity to help you in solving the problems related to what you have covered in this current week. So, every week, this class will be conducted in the same slot. So one class will be on Saturday, one class will be on Tuesday. So whoever wants to join the class, they can join even in both the sessions or one of the session they want. All the materials regarding the means lecture that we have covered in this current week will be provided to you in a Doodle Excel sheet, which will be there in your NPTEL announcement section, from where you can access all the recorded videos as well as the PDF of the session what we have covered in every week. Okay, so let's start this session. So let me share my screen first. I hope everyone will be seeing the shared screen. Can anyone confirm for that?
Yes.
Okay, fine. Thank you. So this is your first class. So what is the purpose of this class? Is like whatever topics that you have covered in every week, related to that, we will try to solve some examples in this. And if you have any queries and doubts what you have covered in this current week, you can ask in this session, or also you have a discussion, or you can say Swayam app in which you can write your query, and one of the TAs of the course will try to give you explanation regarding your query as soon as possible. So this is your first problem solving session in which we will try to cover some problems related to what you have covered in this current week. So talking about the course layout. So course layout contains 12 weeks. So for the 12 weeks, what you are required to cover are mentioned in this slide. So in this current week, you have already covered equilibrium of structures, how you determine the equilibrium of the structures, then how you determine the statically determinate as well as indeterminacy of the structure, and then you have then some examples related to shear force diagram as well as the bending moment diagram for frames as well as for the beams. So this is the week one, is you can say is a considered as a review week, in which what you have covered earlier, or depending upon your knowledge in the previous courses that you have already covered, this is just an introductory section. After that, in the next 4 weeks, from week 2 to week 6, you will be solving the different problems related to statically determinate structures, and from week 7 till week 11, you will be solving the problem related to statically indeterminate structures. So talking about statically determinate structures, you have truss, beams, and frames. So how to solve them? You have different methods. So for truss, you have method of joints and method of sections. Then if you require to find deflections, then you can utilize principle of virtual work. For deflection in beams and frames, you can use moment area method, conjugate beam method, and virtual work method. And finally, giving you an overview about the moving load, you will be solving the problems related to influence line diagram. After that, we will move to statically indeterminate structures, where we will first introduce you with the force and the stiffness method. Then how to solve the problems related to what you have covered earlier, like truss, beams, and frames. Now with indeterminate structures, then you will solve the problem for that. So here also for truss, you will use method of consistent deformations, and for beams and frames, we will use moment distribution method and slope deflection method. So this is the whole layout of the course, and you can say only three things you have to be required to cover. One is beam, another is fray, third is truss. So depending upon their determinacy, whether they are statically indeterminate or indeterminate, what kind of method you require to solve the problem, you need to look upon that and then try to solve that problem. So finally, in the 12th week, what we will do, we will give you an introduction related to direct stiffness method, or you can say matrix method, which you will be using in the structural analysis 2 course. And this will provide you an overview that what is required to be solved in the next course that you will be taking or not taking depending upon your choice. Okay, so what you have covered in this current week, you have started with the idealization of the structures. What do you mean by idealization of the structures? You have the supports available with you, you have the loadings available with you. Now you have to draw the bending moment diagram related to that. That means you have a UDL, how you are converting that UDL into an equivalent load. If you have a UVL, how you are making them into an equivalent structure and then determining the reaction at different points. Then you are applying the principles of static equilibrium. So we have three principles of static equilibrium. So these three equations are summation of forces in horizontal direction are equal to 0, summation of forces in vertical direction are equal to 0, and summation of moment at a particular point is equal to 0. Okay. Then we have seen how to determine the determinacy of the structure. So determinacy of the structure, how you will determine that, one question related to that also we will see in this current session. Then finally, you have seen how to draw the bending moment and shear force diagram for different beams, and then provide what will be the, means you can say journalize if you have the UDL, whether it is a whether the bending moment follows a second degree curve or 1 degree curve, you will see that. Or if you have UVL, so what kind of degree of the bending moment and shear force in that you are seeing. So this is the basics of the loading as well as the supports that you are required to understand in this current week. So talking about questions, what you are required to solve. So I will not be giving you any theoretical descriptions because you have multiple questions to solve in this session. So we will directly jump to the questions and try to solve the problems related to that. If you have any problem in between, you can ask any basic question will be considered. We will try to explain them as in an easy manner as possible. Okay. So anyone can interrupt in between if they have any doubt. We will try to solve your query. Okay. So in this question, what is described to you? You are made to draw the shear force as well as the bending moment diagram for the beam AB, in which you have to consider the sagging moment to be positive and the shear force side upright and down combination as positive. Okay. So this is like you have to draw the shear force and the bending moment diagram for this beam. So first of all, you determine what will be the reactions at point A and point B. So for this, if we make summation of forces in vertical direction to be equal to 0, what you will get? So suppose this is your RA and this is your RB. So since A is a hinge support, so in this one horizontal force will also comes into picture. This horizontal force will be equal to 0 because no horizontal force is acting in this whole system. So you are only available with the vertical forces. So if you are utilizing summation of vertical force is equal to 0, what you will get? RA plus RB equal to 6 plus 6 equal to 12 kilonewton. So now you have two unknowns. You are required to solve the problem. How you will do? You will use another equation, that is summation of moment about point A will be equal to 0. You can use any of these. We can also use summation of forces about summation of moment about point B also equal to 0. So what you will get in this, take clockwise movement as positive and anti-clockwise movement as negative. Okay. So from point A, first load comes is 6 kilonewton. So 6 into 3 plus 6 into 6. Now minus, because RB is in anti-clockwise direction, into 9 equal to 0. So solve this. What you will get? You will get RB equal to 6 kilonewton. Okay. Now substitute this RB in the first equation. So this is your first equation. Okay. So what you will get? RA will be equal to 12 minus 6 equal to 6 kilonewton. Now solve this problem and draw the shear force as well as the bending moment diagram. Okay. So now you already have the reactions. That is, your RA is equal to 6 kilonewton. Your RB is equal to 6 kilonewton. Now, if we draw the shear force diagram, how will it will look like? So you mark the locations where the shear force as well as the bending moment diagram will change. Okay. So let's start making that. So first you have 6 kilonewton. So this 6 kilonewton in the upward direction will be taken as positive. After that, there is no load in between. So this 6 kilonewton will go straight. After that, 6 kilonewton in downward direction. So 6 minus 6 will be equal to 0. Then no force is coming in between. So again, you have 6 kilonewton in downward direction. This 6 kilonewton will continue for further. And after that, final reaction at B is 6. So you got your shear force diagram in this case. So this is your shear force diagram. In this, you can write the upward point to be positive and downward to be negative. Okay. So this is your shear force diagram. Now, how to draw the bending moment diagram? If you know that for this case, since concentrated load is acting upon a point, so what you will get? You will get a linear relationship between moment and the load. So in this point, since 6 is acting, so 6 into the distance, it will go. So at this point, what will be your moment? So your moment at point, suppose this is point C, this is point D. So your MC will be equal to 6 into 3 equal to 18 kilonewton meter. So this will be your 18. No load in between. So in this case, it will continue like that. Okay. And then from this, it will reduce to 0. Or else if you need any other method, what you will do, you will calculate moment at point C, moment at point D. So moment at point D will be equal to, first load is 6 into 6, 36, minus 6 into 3. That will come out to be 18 kilonewton, same. Okay. Again, if you calculate moment at point B, it will come out to be 0. So these are your shear force and bending moment diagram for loads which are acting at a particular section. Okay. So let's move to another question. In this, you are required to calculate absolute maximum shear force and minimum bending moment. It is telling you to calculate the absolute values of the shear force and the bending moment. That means whether the bending moment is positive or negative, it doesn't affect that. You are only interested in the maximum shear force at a particular section. Okay. One major thing that you are required to see in this question, that it is asking for maximum shear force. So where maximum shear force occurs? So maximum shear force occurs where bending moment is minimum. So that means you are required to calculate shear force and the bending moment at one single point where either shear force is maximum or bending moment is minimum. So first what we will do, we will first determine the reaction at point A and point B. So in this case, you have RA plus RB equal to 1 by 2 into W, that is the maximum load in this section, into what will be the length? L by 3. So that will be equal to WL by 6. Now take moment about point A equal to 0. What you will get? So if you try to convert this uniformly varying load into a point load, so this load will come at this point, or I will make it nearby in this point. Okay, and its maximum value will be equal to WL by 6, and this will be at a distance of 2 by 3 into L by 3 equal to 2L by 9 from this point. Okay, from this point. So now calculate reactions at point A and point B. So your RA, RB into L minus WL by 6 is your maximum load. How, where it is acting? It is acting at a distance of L by 3 plus sorry, this will be, I think, 1 by 3. This will be 1 by 3. So this will be equal to L by 9. So in this case, it will be equal to 2L by 9. So here it will be 2L by 9. Okay. This will be equal to 0. Now solve for this. You will get RB equal to W by 6 into 5L by 9. This will be equal to 5WL by 54. This is your RB. Now you are required to calculate RA. RA will be equal to WL by 6. This is your total load minus 5 WL by 54. What you will get? You will get 4 WL by 54. Okay. If you add both of them, you will get WL by 6. Okay. Now try to utilize the concept that where shear force will be maximum. Okay. So let me copy this. I will draw the shear force diagram for this case. So now what reactions you got? In this case, you got RA equal to 4 WL by 54 and RB equal to 5 WL by 54. Now draw the shear force diagram for this case. How it will look like? In this case, 4 WL by 4 will be in upward direction. Okay, so draw this. So this is your 4 WL by 54 and this will be in downward direction. So this will be 5 WL by 54. So till the point where no load is acting, like you can say point C and point D, your bending moment will be constant. Okay. So this is how, sorry, your shear force will be constant. So this is how shear force diagram will look like for beam BC and beam DB. Now you are only required to determine the shear force diagram for beam section B, C and D. How you will do? So let's see. So in this case, how your shear force diagram will look like? If we try to determine at any section HH, so your shear force will be equal to 1 by 2 into WH by L into H by 3 if I am taking from point C. So that will be equal to WH square upon 6L. Fine? Comfortable? Okay. So that means this area will follow second degree curve. So that means in this case, this point will not be linear. So this will be non-linear. So this will be non-linear. So you make the section not to be linear in this case. You try to make it non-linear. Okay. So this is how the bending moment shear force diagram for this case will look like. Okay. So this area will be positive. This area will be negative. Now, if you try to determine what will be the maximum shear force value in this case, so shear force value is coming out to be maximum in this region. Because after that, the loading will start and it will be decreasing. Okay. Or you can say increasing because we are considering only the absolute values. So it can be increasing and it can be decreasing. So your shear force is maximum only in this region. Okay. So we can write that your maximum shear force is equal to 5 WL upon 54. Now we are interested in to determine the minimum bending moment at that particular section, because in this area the shear force is maximum, but at what point this bending moment is minimum, we have to determine that. So in this section, if we make a cut, so if we make a cut in this section like HH, like HH, now you have to determine the moment in this region. Okay. So how you will determine? So your moment at XX will be equal to RB into X. Okay. So what is the value of your RB? Your RB is 5WL by 54 into X. So now for bending moment to be minimum, MXX needs to be minimum. Okay. So when this minimum will come? This minimum will come at X is equal to 0. So at X is equal to 0, your bending moment will be minimum. Fine. So your moment, minimum bending moment at X is equal to 0 will be equal to 5WL upon 4 or 54 into 0 equal to 0 kilonewton meter. Okay, fine. Anyone has any doubt in this? Please ask. Okay, let's continue to another question. So another question is, how many degrees of freedom does a hinge support possess in 2 dimensions? So how you will draw hinge support? So this is your hinge support. So in 2D, how many reactions are there? So if you want to make it into equivalent diagram, so you generally draw 2 reactions. One is horizontal direction and one is horizontal reaction and another is vertical reaction. So suppose this is support A. In this is your vertical reaction, this is your horizontal reaction. Now he's asking you about what would be the degrees of freedom. So in this case, what he is asking you is in how many directions this support can move. So from this you can see this cannot move in horizontal direction and vertical direction. Now in what direction it can move? It can rotate. Okay, so hinge A can rotate. So number of degrees of freedom available for hinge support in 2 dimension is equal to 1. Okay. Now talking about other supports also. So you have fixed support. How you will draw that? So this is your fixed support. So in this case, the total number of reactions that are coming is 1 horizontal reaction, vertical reaction, and 1 is moment. Okay, 1 is moment. So this is your horizontal reaction, this is your vertical reaction, and this is your moment. So in this case, all the 3 are available. So your degree of freedom for fixed support will be equal to 0. Now for roller support, how many reactions are there? Only one single reaction in vertical direction, that will be equal to Ra. So in this case, it can move in horizontal direction also, it can rotate also. So degrees of freedom for roller will be equal to 2. Okay. So this is the concept of degrees of freedom. Now another question is available for you. In this, you have to determine the maximum positive as well as the maximum negative bending moment for this beam. Now he is not talking about absolute values. He is talking about the maximum positive and the negative bending moment that will be obtained in this particular beam section. So what you will do? First you will calculate the reactions. So how many reactions are there? Two reactions are there. One is RB, another is RC. So take summation of forces in vertical direction equal to 0. So you have RB plus RC equal to, you have total load acting on the section in BC section equal to 10 into what will be the length of the member? 5 meter equal to 50 kilonewton. Fine. Now calculate moment about any point. So let's say I am taking in this case moment about point C equal to 0. So in this, take clockwise moment as positive, that is RB into 5 minus 5 kilonewton meter, that is acting at support A. Then you have the bending moment due to this loading. It will come out to be 10 kilonewton into 5, and this will act at a distance of 5 by 2 equal to 0. So your RB will be equal to 26 kilonewton. Now calculate the value of RA. RA will be equal to 50 minus 26 equal to 24 kilonewton. Fine. Now what we will do, now total we have RB equal to 45. Okay. Now we will determine at what point this bending moment is coming out to be maximum. Okay. So take a section XX from T4 now. Okay. So this will be RC. Not RA. So take a section XX from point C. Okay. So let's let this distance be H. Okay. So now we will find moment at XX. So moment at XX will be equal to 10 into H into H square upon 2. Okay. So in this case, since this is carrying a Hodgin moment, so that will be coming out to be negative, plus 24 into H Okay, so this is your generalized moment equation at point x. Now you are required to calculate the value of the bending moment. Okay, so your maximum bending moment will come when we take differential with respect to x equal to 0. This will give you minus 10 into 2x upon 2 plus 24 equal to 0. So from here you can find out the value of x, that will come out to be 2.4 meter. Okay, so that means at x is equal to 2.4, your bending moment will be either positive or negative. Okay, so let's find the value of bending moment at point xx. Okay, so bending moment at xx, where x is equal to 2.4 meter, will be equal to minus 10 into 2.4 into 2.4 divided by 2 plus 24 into 2.4. Okay, so this mxx at 2.4 meter is coming out to be 28.8 kilonewton meter. Okay, so now the maximum value you have calculated. Now talking about minimum value. So minimum value, where it will come? It will come at the support A, because if you draw the shear for bending moment diagram, what you will get? Let's draw the bending moment diagram for this case. So in this case, if we draw the bending moment diagram, what will happen? Since from moment from point C, we have determined this equation. Okay, if we substitute the value of x in this, what you will get? You will get first at x is equal to 0, moment equal to 0. As you increase the value of moment, what you will get? At x is equal to 1, your put x is equal to 1 in this equation, you will get 24 minus 5 equal to 19 kilonewton meter. So that means your moment will be positive in this section. And for UDL, you know it will follow 2D curve. Okay, so in this case, your moment distribution will look like this. Okay, and this zero value will come at a distance of, as we have already calculated, at a distance of 2.4 meter. So let me draw this again. At a 2.4 meter, it will be coming out to be negative. Okay, so how it will go? So your diagram will go like this. At 2.4 meter, your maximum value is coming out to be 28.8. Then it will decrease. Okay, and then it will reach a value of 5 kilonewton meter. So this is how your bending moment diagram will look like. In this, you will get a maximum value of 28.8 kilonewton meter and minimum value of 5 kilonewton meter. So your maximum bending moment or you can say sagging moment is equal to 28.8 kilonewton meter and your minimum bending moment that is your hogging bending moment will be equal to minus 5 kilonewton meter. Fine. Let's solve another problem. In this, he is telling you to determine the variation of shear force along the length of a beam for uniformly varying load. So this is the generalized things that you need to remember, or you can meet also. So, but these are the basic fundamentals you have to know. Okay. So let me draw one uniformly varying load. So this is how your uniformly varying load looks like. Okay, fine. So let's say I will say in this the maximum load is W kilonewton per meter, and this is your total length L. Now, what I will do, I will mark a section HH in this case. Okay, so in this case, let's say this is at a distance of X meter from point A it is at a distance of X meter. Now I have to determine what will be the shear force at any particular point. Okay, so how I will do? So let me write this SSHH equal to. So utilize the property of similar triangles. So at point HH, your value of maximum load will come out to be WH upon L. How I did that? Your maximum value is W divided by L equal to, you have to determine this value. So let's see, I will take this value as P upon X. So what will be your value of P? Your P value will be equal to WH upon L. Fine. Now, in this case, you have to determine the shear force diagram for uniformly varying load. So now you have to determine shear force of this region. Okay. How you will do that? 1 by 2 into what will be the load in this section? WH upon L and what will be the distance is H. Okay. So the area of this diagram will give you the value of shear force. Okay. So if you write it, you will get WH square upon 2L. So this is 2-degree variation. Okay. So in this case, your shear force follows. So I will write here for uniformly varying load, shear force diagram follows 2-degree variation. Fine. Now let's move to another question. So your another question is, you have to determine the degree of static indeterminacy of the beam given below with internal hinge. Okay. Now you know the property of internal hinge. So in internal hinge, here, so suppose this is your internal hinge C. In this case, internal hinge has no shear and zero bending moment. Now talking about static indeterminacy, how you will calculate. So your degree of static indeterminacy is equal to number of reactions minus number of e- equilibrium equations available. Okay. So in this case, how many equilibrium equations are available? First is summation of force in horizontal direction equal to 0. This is your one equation. Second is summation of force in vertical direction equal to 0. Another equation. Third is moment at any particular point will be equal to 0. Okay. So these are the three fundamental equations available with us. Okay. No, but in this case, we have one more equation that is equal to summation of moment about point C, or you can say internal hinge. I will write here internal hinge. This will also be equal to 0. So your degree of indeterminacy will be equal to number of reactions. So how many reactions will come into this picture? First, vertical reaction RA, horizontal reaction RHA, moment MA, vertical reaction RB, horizontal reaction HB, moment MB. Okay. So 3 plus 3, total 6 reactions are there. So 6 minus number of available equations, 4. So your DSE, or you can say degree of static indeterminacy, will come out to be equal to 2. Fine. Let's move to another question. In this case, he is expecting you to determine variation of bending moment diagram along the length of a beam for a uniformly, this will be uniformly distributed load of what order. Okay. Now first draw how the uniformly distributed load looks like. This is your uniformly distributed load. Let's say it is of having load W kilonewton per meter for length L. Now I am interested in at a section XX. So at XX, how you will calculate the bending moment? So your moment at XX in case of uniformly distributed load, it will be equal to, so first we will calculate the load. It will be equal to W into X, and at what point it will act? it will act at a distance of h by 2. Okay. So it will be equal to w h square upon 2. That means of second order. So variation of bending moment diagram for uniformly distributed load will be of second order. Fine. Okay. So let's move to another question. In this, he's telling you to determine the reaction force at A. So now you have to determine the reaction force. Now, question is getting complicated because in this internal hinge C is also coming into picture. So if internal hinge is coming into picture, that means at that point it is having zero shear. So if we divide this whole beam into two parts, so let's say I will first draw part CD. Okay. So this is point C, and it is having a load of 20 kilonewton and having this vertical reaction as RD. Now let's say here vertical reaction is acting upon. It could be vertical, it could be downward also. I am assuming it to be vertical. Okay. So in this case, summation of vertical forces equal to 0. What will come? It will come at RC plus RD equal to 20 kilonewton. If we take moment about point D equal to 0, what will come? RC into 4 minus 20 into 2 equal to 0. That will give you value of RC equal to 10 kilonewton. Fine. Now since you have RC equal to 10 kilonewton meter, that is acting in upward direction. Now if we take another beam section, that is this half section of the beam, let me draw this, or I will copy this diagram. Okay. So let's see, we have this beam. Now what I will do, I will make it till point C. I have taken a shortcut. You have to draw the whole diagram. So now in this case, since in this case RC is coming out to be upward, now your RC will come here in the downward direction. It will be equal to 10 kilonewton. Fine. Now this is your whole section. Now you have to determine the value of reaction at A. So let's say this is RA, this is RB. So taking summation of forces in vertical direction equal to 0. So your RA plus RB will be equal to 5 into 4 for UDL load plus concentrated load of 15 kilonewton plus this 10 which is coming out from internal hinge. If you calculate that, how it will come? Your total value will come out to be 35 kilonewton. Now you have to determine the value of RA. So how you will do? You will take the reaction, or you can say moment about point A equal to 0. Now in this case, take all the clockwise moment to be positive and anti-clockwise moment to be negative. So first comes out to be uniformly distributed load 5 into 4, and it will be acting at a distance of 4 by 2. Fine. minus RB into 4 plus 15 into 6 plus 10 into 8 equal to 0. Okay. If I am taking RB to another side, what will it will come? It will give you 4RB equal to, this will be 80, 5 4 are 20, 22 are 40. This will be 40, 40 plus 90 plus 80. So that means your 4RB will be equal to 210. That means your RB is equal to 52.5 kilonewton. Fine. Now from this we can calculate RA. Therefore, your RA will be equal to, your total load is 45 minus 52.5, that will give you minus 7.5 kilonewton. But you can say how this 7.5 will act. That means whatever direction you choose, it is wrong. So RA will act in the downward direction. Okay, fine. Let's move to another question. So another question is, you have to determine the bending moment at section B. So in this case, you have to determine bending moment at this particular section. Okay. So bending moment at point B. Okay. So your bending moment at point B, how you will calculate? In this region CD, no bending moment is acting. So bending moment will be 0 in this range. So bending moment at B will be equal to bending moment at BC. It will be equal to W, total load W into L by 3, acting at a distance of 1 by 2 into L by 3. It will be equal to W into L by 3 into L by 6. So your moment at B will be equal to WL square upon 18. Okay. But since this moment is Hodgin moment, so this will be your negative moment. Okay. You have to see in which case it is positive and in which case it will be negative. Fine. So let's solve the last question of today. This is, you have to calculate reaction force at support A. Okay. So if you have to find the reaction force at A, given you have the B as the internal hinge, so what you have to do, you have to divide this whole beam into two parts. So for beam BC, I am assuming the vertical reactions to be positive. Okay, so let's say RB and RC having a load of 10 kilonewton at the middle. In this case, you can write RB plus RC equal to 10 kilonewton. Now take moment about point B equal to 0. What you will get? You will get 10 into, what is the distance? 2 meter. 2 minus RC into 4 equal to 0. That means your RC is coming out to be 5 kilonewton. Fine. Now you have to calculate RB. Your RB will be equal to 10, which is the total load, minus 5 equal to 5 kilonewton. Fine. Now, since this RB is acting in the upward direction, so for beam AB, this will act in the downward direction. So see how I will make it. Now I will make this section for section AB. Okay, so suppose this is your section AB. In this, here the load, concentrated load, will be acting as 5 kilonewton. Okay, now you have to calculate the reaction at point A. Okay, so what will be the reaction? So your RA will be equal to 25 into 6 plus 5. That will be equal to 150 plus 5. Let me shift this. And it will be equal to 155 kilonewton. Okay. So this completes your today's problem solving session. If anyone has any doubt, you can may ask right now. I will wait for 2 minutes.
No.
So in this session we have, yeah. Tell me, who's
Please
this?
check the chat box. I'll put a question there.
Sorry. Okay. Yeah. Bob Robert has written, please, how do you introduce what happens like, how can I tell you? If you have a, yeah, if you have a, you can say suspension bridge. If you have a suspension bridge in which you have multiple span in between, so in this case you will provide an internal hinge in between, so that the shear force at that particular section will be equal to 0, and bending moment will not exceed the maximum bending moment carrying capacity of that particular section. So that's how we'll introduce internal hinge at particular section. Okay. Anyone else has any doubt? I'm waiting for your queries. Okay. So what we have solved in this current session, we will solve the problems related to, let me go. Yeah. So what we did in this session, we have solved the problems related to shear force and the bending moment diagram. What's important for you is to know how the variation of shear force and bending moment diagram happens in UDL, UVL cases, as well as in concentrated load cases. If you see the shear force diagram for the concentrated load have zero slope. Bending moment diagram for this Am I audible?
Yes, you are.
Can anyone confirm?
Yes, sir.
Yes, I can hear you.
Okay, okay. So let's summarize the session. What we have done in this case, we have solved the problems related to shear force as well as the bending moment diagram. Then we have seen how to determine the static determinacy and kinematic indeterminacy at any particular session. This will give you an overview of what you have already learned till you have reached in the structure analysis course. Now, from the next session, we will solve the problems related to trusses. So your next session will be how to solve the problems for the trusses, in which we will solve the problems related to trusses using method of joints as well as method of sections. Next, after that, we will solve the problems related to beams as well as frames using moment area method and conjugate beam method and virtual work method, which will conclude your analysis of statically determinate structures. So I think everyone we would have learned how to solve the problems related to shear force as well as the bending moment diagram and to determine the indeterminacy in the structure. And if you are required to calculate the degree of kinematic indeterminacy or degree of freedom at particular beam, how you will calculate, we have seen in this session. So thank you everyone. Have a nice day. Enjoy your weekend.
This will